The previous lecture dealt with finding shortest paths within graphs. This lecture focuses on detecting cycles within graphs. So the first question we have to answer is, what is a cycle within a graph? Well, let's answer that question by means of a practical example. So let's imagine that you're a software developer. You've developed a software package, and this software package has dependencies. So if one software package has a dependency on a second software package, it means that before the first software package can be installed, the second software package must first be installed. And of course, that software package may have its own dependencies as well. So we of course want to keep track of package dependencies, and we can do this by means of a graph data structure. So here's a fairly simple graph data structure, a directed graph, simply to illustrate this concept. So each of the individual vertices, for instance vertex A and vertex B over here, represent software packages. So for example, software package A may be the software package that we've developed, and there are then other software packages that A depends on, and potentially those software packages may have further dependencies as well. So the way that we're going to interpret this graph is that the directionality of an edge indicates a dependency. So for instance, if we look at software package B over here, there's an edge that connects its vertex to the vertex for software package C. So this means that package B needs package C to be installed first before package B can be installed. In other words, there's a dependency between the two packages. Similarly, before we can install package D, we need to install package B. And to install package A, there are three dependencies. So first of all, we must install package B, then we must install package C, and we must also install package D. So this is relatively straightforward, and we can see that we can successfully install our software package in this case. If we install software package C first, which has no dependencies, then we can install software package B, then we can install package D, and then finally we can install the package that we've developed, package A in that case. So let's add then an additional software package E, represented by this vertex over here, and it also has then dependencies. So what then happens if C depends on E, as we see over here, and also E depends on package B? Well, here we have a problem, because to install E, we need to install B first of all, but B needs C to be installed, and C also needs E to be installed, which can't be installed yet because it requires B to be installed. So this kind of structure is then referred to as a cycle, and more formally defined, it's a path that arrives back at its start, where every vertex is unique. So we can see within this cycle, if we, for example, start with vertex B, then we travel through C and E, and then back to B again, and each of the vertices on that circular path there is a unique vertex. So oftentimes we want to be able to detect these cycles so that we're aware of them. And for example, in the case of a package system, we may want to then warn a user or a developer that there is a circular dependency which is going to prevent the package from being built. As for shortest path detection algorithms, there are once again several different ways that we can detect cycles within graphs. Now, the first approach that we're going to look at is based on the all-to-all shortest path detection algorithm that we discussed right at the end of the previous lecture. And as you should recall, that algorithm is referred to as the Floyd-Warshall algorithm. If you need to revise the operation of that algorithm, I recommend that you do that at this stage. So we're essentially going to take the basic structure of the Floyd-Warshall algorithm and just slightly modify it so that it is able to detect cycles. All right, so just to revise the general outline of the algorithm, over here we have an example graph that we're going to use for the illustration of how this algorithm operates. So again, there are vertices, we have edges, and we have costs that are associated with those edges. Now, it is important for the operation of the Floyd-Warshall algorithm for cycle detection that there must be costs associated with the edges. So to begin with, we then have to initialize an adjacency matrix. And we can see the initialization over here. So we set up an adjacency matrix of the correct size. However, what is very important to note here is that we leave out the step that initializes the values on the diagonal of the adjacency matrix to 0. So this is then our initial adjacency matrix. You can see that we have a row and a column for each individual vertex within this graph, and we've initialized all of the values within the graph to infinity, but notice that the values on the diagonal are not set to 0. So then we do an initialization of the initial distance values within our adjacency matrix. And what we do here is for each edge, we then simply add the appropriate distance value for that single edge. So for example, this edge that links vertex A and B, you can see has a distance value of 2. So if we look at vertex A connected to vertex B over here, we add a value of 2 there, and that indicates that path connection. So we do this for all of the edges within this graph structure. And once we've done that, we then have an initialized adjacency matrix. We now get to the main body of the Floyd-Warshall algorithm. So that's represented by means of these 3 nested for loops with an if statement nested inside them. Now, the operation of this then hinges on the 3 loop control variables, I, j, and k within these for loops. So each of these loop control variables represents a vertex within the graph. So what we're checking then is for each iteration, given vertices I, j, and k, can we find a path that connects vertex j to vertex k, but if it goes through vertex I, we then have found a cheaper or lower cost path. Now, if we have found such a cheaper path, then we update the appropriate value in the adjacency matrix with that cheaper path value. So as we did in the previous lecture, we will look now at the operation of this algorithm by looking at each of the iterations of the outer loop. So on the first iteration, I takes on a value of 1, which means that we're dealing with vertex A. So we're testing to see, are there any paths between 2 vertices that if they connect through vertex A, we then have a shorter path. Now, if we look at our graph over here, we see that it is a directed graph, and we see that no vertices connect up to vertex A. So this means that there are no paths that run through vertex A. We can only use vertex A as a source point to move along a path from. So because there are no paths that move through vertex A, this means then we can't find shorter paths using vertex A, and therefore no values in the adjacency matrix are updated. So if we move on to the second iteration of the outer loop, I takes on a value of 2, which means that we're working with vertex B in this case. So we're testing to see, are there any paths that if they go through vertex B, we found a shorter path. So we can see that if we move from vertex A to vertex C, on the previous iteration, the shortest path was 6, and you can see that's reflected in the adjacency matrix for the previous iteration with that value 6 at the intersection of A and C over there. So we see that if we move from A to C, but instead of using the direct connection, we now move through vertex B, we found a shorter path, and that path has a cost of 2 plus 3, which is 5, which we insert at that location, the intersection location, within our adjacency matrix. We can also see that if we move on a path connecting vertex D to vertex C, if we look at that intersection for the previous iteration, that value was infinity. This means that at that point no connection could be found connecting vertex D to vertex C. However, we can see that if we move from vertex D to vertex C, but we go through vertex B, we now have a path connection, and the cost is -1 plus 3, which gives us a value of 2, which we insert into our adjacency matrix. We now move on to the third iteration, so I takes on a value of 3, meaning that we're working with vertex C at this point. And we can see for vertices B and D, on the previous iteration, the cost for the path from B to D was infinity, meaning that there is no such connection path. However, if we now go through vertex C, and we're moving from vertex B to vertex D, then we can see that moving through C, we now have a path that connects those two vertices, and the cost of that path is 3 plus 5, which gives us a value of 8, which we can insert into the adjacency matrix at that point. Now, with our original formulation of the Floyd-Warshall algorithm, we didn't update any values on the diagonal. However, for our cycle detection implementation, we do update such values. So if we consider vertex D connecting to vertex D itself again, we can see that we can find a path back to D again as long as it goes through C. So we need to go through vertex B. We've already considered vertex B on the previous iteration, and then through vertex C, which we're currently considering, and then back to D again. And the cost of that path is -1 plus 3 plus 5, which gives us a value of 7, which we insert over there in our adjacency matrix. Now, as soon as we update a value on a diagonal, this then indicates that we've found a cycle, and in this case, the cycle is a cycle that connects vertex D back to itself again. So let's move on to the next iteration. Over here, I takes on a value of 4, meaning that we're working with vertex D. So we're looking for paths that go through D that then form shorter paths connecting two vertices. So we can see we have quite a number of those situations. If we look at vertex A connecting to vertex B, we saw in our previous iteration that that cost was 2. That's the direct link between A and B over there. However, we can see we can also move from vertex A to vertex B going through vertex D, and the cost there is 1 plus -1, in other words, cost of 0. So we found a shorter path, and we then update that value in our adjacency matrix. We can also see that connecting from vertex A to vertex C, we had initially a cost of 5 on the previous iteration, but if we go through vertex D, then if we connect vertex A to vertex C, but we go through D, we now have a cost of 1 plus -1 plus 3, which gives us a cost of 3, and that's lower than the previous cost. So we replace that value in our adjacency matrix. Also, if we look at vertex C connecting to vertex B, we can see in our previous iteration that the value for that connection was infinity, meaning that no such connection was possible yet. However, if we connect C to B, but we go through D, so we are moving from C to vertex B, but we're going through vertex D, we now have a cost of 5 plus -1, which gives us a cost of 4, which is lower than the previous cost, so we replace that value in our adjacency matrix. Now we can see additionally we have two cycle connections. And these are then, first of all, the connection from vertex B to vertex B. We can see that if we move from vertex B to vertex B going through vertex D, so we can see that that path involves C and then D connecting back to B again, then we have a cost for that path. So that path is then 3 plus 5 plus -1, which gives us then a value of 7. And once again, we've updated a value on a diagonal, so that means we've detected a cycle that connects B back to itself again. Finally, we have vertex C connected to vertex C, and we can see that once again there, if we go through vertex D, we then have a connection with a cost of 5 plus -1 plus 3, which gives us then a cost of 7, which is inserted at that point in our adjacency matrix. Again, we've updated a value on a diagonal, so this means that we have a cycle that connects vertex C to vertex C. We've already looked in the previous iteration at the cost connecting D to D, which we saw was also 7 at that point. So we've detected cycles. However, what's important to understand here is we can detect that cycles exist fairly easily, but actually reconstructing the cycle path is a little bit more difficult. It is possible for us to do that with a fairly minor modification to the Floyd-Warshall algorithm, but that's beyond the scope of what we're going to be discussing for this lecture. So we've seen that the Floyd-Warshall algorithm works in terms of being able to detect cycles, but it is fairly inefficient, as well as not being able to reconstruct the path of the cycles very easily. The second cycle detection algorithm that we're going to discuss is based on the depth-first search algorithm. So over here we have the pseudocode for the depth-first search algorithm. This was covered in the first lecture for this chapter, and if you need to revise that material, I recommend going back to it at this point. So essentially the operation of the depth-first search for a graph works by iterating over all of the vertices within the graph. And then for each of these vertices, we then iterate through all of the vertices that are adjacent to that vertex. Now, what's important to understand here is we have this data structure called edges, which is initially empty. And each time that we visit a vertex within our graph, we then attach the edge that we've traversed to the edges data structure, and then finally we output the edges data structure. Now, for this cycle detection, we're not interested in a full traversal. We're only trying to detect cycles and output those cycles. So we're going to do away with this edges data structure and make a few more modifications to the algorithm. So we are now going to consider a modified depth-first search algorithm that allows us to detect cycles within a simple undirected graph. In other words, the edges in this graph are not directed, so they are essentially bidirectional. So over here we have the pseudocode for this modified algorithm, and if we look at the pseudocode, we can see that the majority of it is exactly the same as the original depth-first search algorithm that we discussed in the previous slide. There are, however, some modifications, and those are indicated in red over here. Alright, so at this point we need to take note of the fact that, like the original depth-first search algorithm, for every vertex within the graph, we have a number variable associated with it, and that number indicates the order that the vertex has been visited in during the search. But in addition to this number, we also have for every vertex a predecessor, and this is simply the name of another vertex within the graph. So let's look at the operation of this algorithm in terms of a practical example where we apply the algorithm to this graph over here. So to begin with, we execute this for loop. This for loop iterates over all of the vertices in the graph and sets the number for each vertex to 0, as you can see over there. We also have this global count variable I, and its initial value is 1. We then enter this loop over here. So this loop iterates over all of the vertices that exist that still have a number that has a value of 0. Now, if we look at this graph, we can see that every vertex has a number of zeros. So we could, at this point, for the first iteration of this while loop, select any vertex within the graph. But to simplify our discussion, we're going to work alphabetically through the vertices. So in other words, the first vertex that we will select for the first iteration of this loop will be vertex A. We then call the cycle detection DFS function, which is a recursive function, and we pass through this vertex that we have selected. So in other words, the selected vertex is then vertex A. So now we've entered the cycle detection DFS function. The first thing that we need to do is we need to update the number for the current vertex that we are looking at. So we set that number to i's current value, and then we increment I. So note, this is a post-increment operation, meaning we assign the value of I first, and then we increment I after the assignment has taken place. So to do that, we then update the count of vertex A, and we update it to i's current value, which is 1, after which we increment i's value to 2. So now that we've updated this number, we enter this for loop over here. This for loop iterates over all of the vertices that are adjacent to vertex V. In other words, at this point during the algorithm's execution, all of the vertices that are adjacent to vertex A. Now if we look at vertex A, we can see that there are 3 adjacent vertices. There's vertex B, vertex C, and vertex F. And again, we could select any one of those 3 vertices as the first adjacent vertex that we will consider. But again, we're going to work in alphabetical order, so that means the first adjacent vertex that we select will be vertex B. So we've now selected vertex B. We now need to look at the number of this adjacent vertex, vertex B, and test to see whether its value is 0. Well, we can see for vertex B its number is 0, so therefore we enter this if statement, and now we need to set the predecessor for this vertex to the current vertex V. So in other words, we're setting the predecessor for vertex B, and we're setting that to the current vertex A. And we've done that over there. We now call the cycle detection DFS function once again, but now we pass through this adjacent vertex that we've selected. In other words, in this example, vertex B over here. So now for the next execution of the cycle detection DFS function, our vertex V is now updated to vertex B. So now we just perform the whole process again. First of all, we have to update the number for vertex B to i's current value, which is 2, and we increment i's value to 3. Now that we've incremented the number, we need to consider the vertices that are adjacent to vertex B. So we can see that there are 3 such vertices, vertex A, vertex E, and vertex G over there. Now, this condition over here, the second condition within the cycle detection DFS function, prevents us from visiting the predecessor of the current vertex. So the predecessor of the current vertex is A, meaning that we ignore vertex A, so we are only considering vertices E and G. So again, we work alphabetically, meaning that the next vertex that we consider is vertex E. And again, we look at the number for vertex E. We see that that is 0, so we need to then set the predecessor of vertex E to the current vertex, which is B in this case. So now we move on to the next execution of cycle detection DFS. We're now working with vertex E. So we need to update the number for vertex E, and we update that to i's current value, which is 3, and then we increment I to 4. So now, once again, we need to consider the vertices that are adjacent to vertex E. We again ignore the predecessor vertex B, so we are only considering vertices D and G at this point. Again, we work alphabetically, so we will be selecting vertex D. And we then need to look at the number associated with vertex D. We see that that once again is 0. So we now need to set the predecessor of vertex D to the current vertex, which is E. So at this point, we now move to the next execution of the cycle detection DFS function. So at this point, the current vertex that we're considering is vertex D. So at this point, we then need to update the number for the current vertex D to i's current value, which is 4, and then we increment i's value to 5. Now we again need to consider all of the vertices that are adjacent to vertex D. Again, we ignore the predecessor vertex, so we are only considering vertices G and H at this point. Again, we'll work alphabetically, so we move on to vertex G. We look at vertex G's number, which is 0 once again, so we have to set its predecessor to the current vertex, which is D, and then we move on to the next execution of the cycle detection DFS function, so the current vertex that we now consider is vertex G. So now, again, we need to update vertex G's number. We update it to i's current value, which is 5, and we increment i's value from 5 to 6. Now we need to consider vertex G's adjacent vertices. Again, we ignore the predecessor, so we see that we have 3 adjacent vertices, vertex B, vertex E, and vertex H. So again, we will work alphabetically, so the next adjacent vertex that we select is vertex B. So now we need to look at the number for vertex B. We see that it is not 0. It's also not the predecessor vertex for the current vertex G. So therefore, we enter the body of this second if statement over here. So again, we update the predecessor to the current vertex. So we can see then that B's predecessor gets updated to the current vertex G. And then we detect a cycle, and we need to report that cycle that we've detected. Now, to report this cycle, we use the predecessor vertices starting at the current adjacent vertex that we are considering, in other words, vertex B at this point. So we start off with vertex B, we look at its predecessor, which is vertex G, so we move to vertex G. We look then at its predecessor, which is vertex D, so we visit vertex D. We look at its predecessor, which is vertex E, so we move on to vertex E. And then finally, we look at E's predecessor, which is B, which takes us back to the first vertex in the cycle. So here we have then our cycle with a succession of vertices that we visited in order by means of the predecessor vertices. So we report that cycle, and now we are done with adjacent vertex B. So we're still working with vertex G at this point, but now we need to move on to the next adjacent vertex. So we have 2 adjacent vertices, vertex E and vertex H, and the next one that we are going to select is vertex E. So again, we need to then look at vertex E's number. We see that that number is 3, so it is not 0. This vertex is also not the immediate predecessor of vertex G, so therefore we need to set its predecessor to the current vertex, in other words, vertex G. So now we have updated the predecessor, and now we need to report that we have found a cycle. So once again, we do that by working through the predecessors. We start off at vertex E. Its predecessor is G, so we visit vertex G. Its predecessor is D, so we go back to vertex D. Its predecessor is E, so we move back to vertex E. That completes our cycle, and we then report that cycle. Right, so now we've considered adjacent vertex E. We now need to consider the last adjacent vertex for vertex G, and that is vertex H, as we can see over here. So now we need to look at the number for this adjacent vertex. We see that it is 0. So we set then the predecessor of this vertex to the current vertex, which is G, and now we go into another recursive execution of the cycle detection DFS function. So in other words, the current vertex now updates to H, which is the vertex that we're currently looking at. And the first thing that we have to do is we need to update the number for this vertex. So we update the number to the current value of I, which is 6, and we increment i's value to 7. So now we need to consider all of the adjacent vertices for vertex H. We ignore G because that's the immediate predecessor of H. So we only need to consider vertex D at this point as an adjacent vertex. So now that we're considering vertex D, we once again need to look at D's number. And we see that that's 4. In other words, it's not 0. D is also not the predecessor of the current vertex H. So therefore, we set its predecessor to the current vertex, in other words, H. And now we need to report a cycle. And once again, we work then through the predecessors in order. So we are now at vertex D. We see that its predecessor is vertex H. So we move back to vertex H. Its predecessor is G, so we move back to vertex G, and its predecessor is once again vertex D, so we move back to vertex D, and now we have a full cycle which we report over there. All right, so at this point we have then finished execution for the current vertex H, and we've considered all of its adjacent vertices. There are no further vertices to consider. So now we need to move back to the previous iteration, in other words, or the previous execution of the cycle detection DFS function. In other words, we are unwinding the stack, so we go back to vertex G at this point. Now looking at vertex G, we see that we have considered all of the adjacent vertices for vertex G. So we unwind the stack once again, and we now go back to vertex D. Vertex D, once again, we see that all of the adjacent vertices have been dealt with. So we unwind the stack further back to vertex E. Looking at vertex E's adjacent vertices, we see that they've all been considered. So we unwind the stack further to vertex B. And again, the same holds for vertex B. All of its adjacent vertices have been considered. So we finally unwind the stack all the way back to vertex A, which was the first vertex that we considered. So now we've finished dealing with vertex A and its adjacent vertex B. So now we need to consider the next adjacent vertex for vertex A, and that will be vertex C. So now we look at vertex C's number, which is 0. So we need to set the predecessor of C to the current vertex, which is A, and then we move on to the next execution of the cycle detection DFS function, where the current vertex that we are now considering is vertex C over here. So now we need to consider the adjacent vertices for vertex C, but before we can do that, we need to update the number for vertex C. So we update that to the current value of I, which is 7. We increment i's value to 8, and now we can consider the adjacent vertices. Again, we ignore the immediate predecessor, so we only have to consider vertex F at that point. So now we look at vertex F's number. We see once again that it is 0, so we need to set its predecessor to the current vertex, which is C. And then we move to the next execution of the cycle detection DFS function, but now for vertex F. So now we need to once again update the number for vertex F. So we're updating that value 0 to the current value of I, which is 8. We increment i's value to 9, and now we need to once again consider all of the adjacent vertices for vertex F. So again, we ignore the immediate predecessor. We then only need to consider the adjacent vertex A at this point. So that's the vertex that we're considering. We now need to look at A's number, and we see that it is not 0, which means that we have now detected a cycle. So we set the predecessor of vertex A to the current vertex, which is F, and then we work backwards once again through the predecessors from vertex A to determine the vertices that are contained in the cycle. So we start off with vertex A, the predecessor there is F, so we move to vertex F. The predecessor for vertex F is vertex C, so we move back to vertex C, and then the predecessor for vertex C is vertex A. That completes our cycle, and now we can report that cycle. Alright, so now we have finished considering for the current vertex F all of its adjacent vertices. So now we need to unwind the stack. So we go back to vertex C. We see again that for vertex C there are no adjacent vertices that we can still consider. So we unwind the stack further back to vertex A, and we see that for vertex A there are no further adjacent vertices that we need to consider. So at this point the algorithm terminates and we have reported all of the cycles that exist within this graph. So on the previous slide we discussed a modified depth-first search algorithm for the detection of cycles in an undirected graph. We're now going to apply the same procedure but to a directed graph. Now some minor modification is required once again to the algorithm, and it's highlighted again in red over here. And the reason that this modification is required is that we're going to limit our cycle detection search to the current spanning tree. So the modification involves, for a vertex V, after we have finished considering all of the adjacent vertices for vertex V, we then set V's number to infinity. And this infinity value indicates that the vertex is on the current spanning tree and should therefore not be considered for further cycle detection. Additionally, the condition of our second if statement over here is changed to test whether the number for the current adjacent vertex that we are considering is not infinity. In other words, that the vertex is not in the current spanning tree. Alright, so once again, let's apply this algorithm to an example graph over here. Note that this graph is a directed graph, so the edges are directed with, for each edge, a specific source vertex and a destination vertex. Alright, so the initial execution of our algorithm is exactly the same as we saw for the algorithm example that we looked at on the previous slide. So once again, we have to initialize the numbers for every vertex in the graph to 0, and we set the global I counter to a value of 1. We then need to select a vertex. So again, we're going to start with vertex A at this point, and then we call our recursive function on vertex A. So this means we have to first of all update the count for vertex A. We update it to i's current value, which is 1, and we increment i's value to 2. So now we need to consider the vertices that are adjacent to A. These vertices are vertex B and vertex C at this point. Again, we're going to work alphabetically, so we are going to select vertex B, and we then look at B's number, which is 0, and therefore we update the predecessor of vertex B to the current vertex, which is A at this point. So now we call our recursive function again, meaning that the current vertex that we are considering is now vertex B at this point. And we now need to update the number for vertex B. So we update that to i's current value, which is 2. We increment i's value to 3. And now we've updated the number, so we need to consider the adjacent vertices. Well, of course, we don't need to consider the direct predecessor because we don't have an edge that connects B to the predecessor. However, we do need to consider vertices E and G at this point. So again, we are going to work alphabetically. the next vertex that we select, the next adjacent vertex, is vertex E, and we need to look at vertex E's number, which we see is 0. We therefore need to update E's predecessor to the current vertex, which is B, and then we call our recursive function again, and now the next vertex that we are considering is vertex E. So considering vertex E, we need to update our number to i's current value, which is 3, and we increment I to 4 at this point. Now we need to consider vertex E's adjacent vertices, and we see we only have one, which is vertex G at this point. So that's the next vertex that we consider. We then look at the number for vertex G, which we see is 0, so we need to set then the predecessor for vertex G to the current vertex, which is E at this point. We then call our recursive function again, so now the vertex that we are considering is G, that's the current vertex, and we need to update the number for vertex D, G. So we update then G's number to i's current value, which is 4, and we increment I to 5. So now we have updated the number variable for vertex G. We now need to look at the adjacent vertices for vertex G, and we see that we only have vertex D to consider at this point. So that's the next vertex that we'll consider. We look at D's number, which is 0 at this point. So this means we need to set the predecessor for vertex D to the current vertex, which is G at this point, and then we call our recursive function again. So now the current vertex that we are considering is vertex D. So now we need to update the number again for vertex D. We update it to i's current value, which is 5, and we increment i's value by 1. So now we have finished updating the number for vertex D. We now need to consider the adjacent vertices again, and we see that we only have vertex E to consider at this point. So that's the next vertex that we will consider. For vertex E, we then look at its number, and we see that the number is not 0, but we also see that the number is not infinity. So this means that we have then detected a cycle. So the first step, as for the previous algorithm, is we need to update the predecessor of vertex E to the current vertex, which is D in this case, and now we report a cycle. So again, we are going to go through the predecessor vertices from the current adjacent vertex that we're looking at, vertex E. So we see that we start off then with vertex E. We then move to its predecessor, which is vertex D. Then we see that the predecessor is vertex G, so we move to vertex G, and then to its predecessor, which is vertex E, and there we've completed our cycle. So we report our cycle. However, notice that the order that we report the cycle in must obey the directionality of these edges. So we visited these vertices in the order E, D, G, and E, so we report these vertices in the opposite direction. All right, so now we've detected our first cycle. Now, because we are still dealing with vertex D, we see that we have considered all of the adjacent vertices for vertex D, so now we need to set its number to infinity, indicating that it is on the current spanning tree. So then we unwind the stack back to the previous vertex that we were dealing with, vertex G at this point. And again here we see that we have dealt with all of the adjacent vertices for vertex G. So we set its number again to infinity, indicating that it is on the current spanning tree. We then unwind the stack again back to vertex E, the previous vertex that we considered, and again we see there are no adjacent vertices from vertex E that still need to be considered, so we set its number to infinity. We then again unwind the stack further, so now we are back to vertex B at this point, and we see that we've considered one adjacent vertex for vertex B, but there is still another adjacent vertex to consider, vertex G at this point. So now we need to consider vertex G. We look at vertex G and we look at its number. We see that the number is not 0, but it is also infinity, meaning that we don't execute either body for either of these two if statements over here. So that means we have then considered all of the adjacent vertices for vertex B, which means we can then set its number to infinity. We then unwind the stack one more step, and now we are back at vertex A. So now we've dealt with vertex A and its first adjacent vertex, which is vertex B. We now need to deal with its second adjacent vertex, which is vertex C at this point. So now we look at vertex C's number. We see that it is 0. So we need to set the predecessor for vertex C to the current vertex, which is A at this point. So now that we've set the predecessor, we now move on to the next execution of our recursive function, meaning that the current vertex that we are considering is vertex C at this stage. So now that we're considering vertex C, we need to update its number. So we update that number from 0 to i's current value, which is 6, and we increment i's value to 7. So now we've updated the number, we need to consider adjacent vertices for vertex C. We only have one adjacent vertex, which is vertex F at this point, so that's the vertex that we will consider. We look at the number associated with vertex F, and we see that it is 0, so we need to set its predecessor to the current vertex, which is vertex C. And now we move on to another execution of our recursive function, and we are now dealing with vertex F over here. So now the next step is we need to update the number for vertex F. We update it to i's current value, which is 7, and increment i's value to 8. And now we need to consider the vertices that are adjacent to vertex F, and we see there's only one adjacent vertex, which is vertex A at this point. So that's the next vertex that we will consider. We look at the number for vertex A, and we see that it is not 0, and it is also not infinity, meaning that we have now detected a cycle. So we deal with the cycle again, just as we did before. We set the predecessor of vertex A to the current vertex F at this point, and then we follow the predecessors. So again, we start off at vertex A, we look at its predecessor, which is vertex F, so we move back to F. Its predecessor is C, so we move back to C. C's predecessor is A, so we move back to A, and that is then our full cycle. Once again, we have to report the cycle in reverse order because we have to consider the directionality of the edges. So now we've located the second cycle, and then because we have finished considering all of the vertices that are adjacent to our current vertex F, we set F's number to infinity, indicating that it is on the spanning tree. We now unwind the stack, so we go back to vertex C, which was the previous vertex that we were considering. We see that there are no further adjacent vertices that we need to take care of. So this means that we set C's number to infinity, and then we unwind the stack once again, and now we are back at vertex A. So at this point, we see that we have considered both of the adjacent vertices for vertex A. There are no further adjacent vertices to consider. So A's number gets set to infinity, meaning that we have now added it to the spanning tree. So at this point, we are now back at this while loop right at the start of the algorithm. And we see that we have now dealt with our first vertex A, and we now need to determine, are there any further vertices that have a number of 0? Well, we see that there is one more vertex with a number of 0, and that is vertex H that we now need to deal with. So we now consider vertex H. So our current vertex is H over here. And we then need to update h's count value to the current value of I, which is 8, and we increment i's value from 8 to 9. So now that we've updated h's number, we now need to consider the vertices that are adjacent to h, in other words, vertex D and vertex G at this point. Now, we see first of all then vertex D has a number which is infinity, so it is neither 0 nor a non-infinity value. In other words, it's a vertex that is within the current spanning tree, so we ignore that vertex. And the same happens for vertex G, which also has a number value which is set to infinity. So for vertex H, there are no adjacent vertices that we need to consider. So we then set vertex H's number to infinity, and this then exhausts all of the vertices. There are no further vertices in the graph that have a number of 0, so the algorithm terminates at this point. So all of the cycle detection approaches that we've discussed so far have worked by iterating over the vertices within a graph in order to detect cycles. Alternatively, we can use set theory in order to detect cycles, and this approach is referred to as the union-find cycle detection approach. So vertices then that are connected by means of edges form a set, and we are going to build up sets of connected vertices. So we need a structure that stores a set associated with each vertex. And each set is a circular linked list, and each vertex set initially contains then only the vertex itself. And each set is identified by means of a number. So for each set, we need to store two values. First of all, a number representing the vertex that is the root of the set, and secondly, a number that represents the next vertex within the set. Right, so this is what the structure would look like for a fairly simple graph. This is the graph over here. So you can see we have 4 vertices, and we have edges that connect these vertices, and this is an undirected graph once again. So our storage structure then is essentially 2 parallel arrays, one there and one there. And if we look at the indices or the subscripts, we can see obviously these are numeric subscripts, but each of them relates to a specific vertex. So index 0 relates to vertex A, index 1 to vertex B, index 2 to vertex C, and index 3 to vertex D. So then at these indices, we have then a root and a next value. And we can see that we initially then set these values at index 0, both to 0, at index 1, both of them are set to 1, and so forth through the structure. What this means then is we have the following set structure over here. So for vertex 0, in other words vertex A, the root of the set is A itself, and the next vertex within the set is vertex A itself. And the same holds then for vertex B. So for vertex B, its root is 1, in other words vertex B itself, and its next vertex is also 1, in other words vertex B itself. The same holds for vertex C and for vertex D. So this is the initial state that we begin this algorithm's execution with. So given this initial data structure, we can then begin with the actual execution of the union-find cycle detection algorithm. So we iterate then through all of the edges that exist within the graph. And for every edge that connects vertex V and U, this tells us that vertex V and U are part of the same set. So this means then that we can update our structure, and for this edge that connects vertex V and U, we must then join vertex V and U into a single set. So we do this by first updating the root of U set to the root of V set. And this makes sense because both vertices are now in the same set, therefore their sets must have the same root. Secondly, we swap the next vertices for V and U within our structure. And this is because V's set now links to U's set, and U's set now links to V's set. So if we then find an edge that connects vertex V and U, where V and U are already in the same set, then we know that we have detected a cycle, and that cycle contains edge VU. Now we can detect this if we reach a point where we need to merge two sets, but those two sets have the same root. So what does the execution of this algorithm look like? Well, over here we have our data structure in its original form that we initialized it to previously, and here we once again have the visual representation of what this graph looks like. So we can see that each vertex exists within its own set. So now we need to consider the edges in order. Now we could consider the edges in any particular order, but we're going to start off with edge AB to begin with. In other words, this edge over here that connects vertex 0 to vertex 1. So now what we need to do is we need to look at these two sets, and we need to determine whether they have the same root. So in other words, we are looking at sets A and B over here and looking at their roots to see whether those roots are the same. Well, of course, they aren't. Set A has a root of 0 and set B has a root of 1. So because the answer to that question is no, we then need to merge the sets. So we do this by setting the root of B to the root of A, which we've done over here. So now the root of B is the same as the root for A, and we need to swap the next values for A and B. So in other words, these two values need to swap, and you can see that that's what we've done over here. All right, so what does this look like then in terms of our actual graph? Well, we can see that sets C and D are still within their own sets. They are not connected to any other sets. However, we have joined sets A and B over here. So both of them have a root of 0. However, set A's next is 1, in other words, B. So we have this connection over here. And then set B's next is 0, in other words, vertex A, which is that connection over there. So we can see that we've linked these two vertices by means of a kind of a linked list structure that is represented within this table, and we've now linked those sets together, indicating that they are connected by means of a vertex. So this is then the point on the previous slide that we left our structure at, and the graph representation of that. So now we need to move on to another edge. And again, we could consider any particular edge, but we're going to consider edge AC at this point. In other words, this edge which connects then set 0 and set 2 together. So now we need to check whether the two sets for A and C have the same root. So we're considering set A and set C. We look at their roots, and of course we see that those roots are different. So the answer to that question is no, meaning again we have to then merge our sets. So we do this by setting the root of C to the root of A, which we can see over here. So the root of C becomes 0. And we then swap the next for A and C. So the next for A and C over here, and we can see this is the structure that we end up with. So what does this graph then look like? Well, over here we have our graph. So we then have the set for set A. Its next is 2, in other words, vertex C. So A connects now to C. Then we see for set C, its next is 1, in other words, vertex B. So we have this connection over here. And then for vertex B, we see its next is 0, in other words, vertex A. So we've connected through there. And that is then our full set. So again, you can see we have a circular linked structure that is represented. So this is once again then the structure that we ended with in the previous slide, as well as our graph representation of that structure. So now we need to consider another edge that we haven't considered before. We're going to presume that the next edge that we look at is edge BC. In other words, the edge that connects set 1 to set 2 over here. So we need to once again determine, do they have the same roots? So we're looking at B and C, and we look at these roots and we see that they are both 0. So that indicates then that we have found a cycle and we need to report it, and we do this by means of following then the next links, and we will start at vertex C at this point. So we start off at vertex C, its next points to B, B's next points to A, and A's next points back to C again. And that is then the cycle that we have detected. So at this point, we've actually detected the only cycle that exists within this graph, but let's just take the algorithm to its final conclusion. So once again, here we have the structure and the graph representation of that structure from the previous slide. So now we're going to consider the final edge, in other words, edge CD, in other words, connecting sets 2 and 3 to one another. So we now need to look at sets C and D. We need to look at the roots and determine whether they're the same. Well, we can see that these sets have different numbers for their roots. So the answer to this question then again is no, meaning that we can then merge the sets together. And we do this then by setting the root of D to the root of C. So we see that we have done that over here. We've set the root of D to 0, which is the root of C. So now all of the sets share the same root. And this makes sense, of course, because all of the vertices are connected to one another. And then finally, we need to swap the next of C and D. So we see that we need to swap this 1 and this 3 over here. And so we've updated those values in our structure. So what does this then finally look like in terms of our graph? Well, we have then vertex A, which is connected to vertex 2 by means of its next. Vertex C is connected to vertex D by means of its next. D is connected to vertex B by means of its next. And B finally is connected back to vertex A by means of its next. So we can see now we've joined all of the vertices together into one set, which is represented by this circular structure over here. That concludes then our discussion on cycle detection. And in the next lecture, we will be looking at detecting connectedness within a graph data structure.